This lecture is all about severe weather. So we're going to start out with storms, thunderstorms, then we'll talk about tornadoes, and we'll finish up with hurricanes. And then after that, we just have climate and climate change left. So this is a map basically showing the average number of thunderstorm days per year. So if it's the greener colors or the more orange and red, that's higher average number of days with thunderstorms per year. So just if you look across the US, there's a couple places in the US that have less than 10 thunderstorms every year. Up here in New England, we might have 10 to 30 thunderstorm days per year. So let's talk about how a thunderstorm forms. There's kind of three ingredients that you need to create a thunderstorm. So you need moisture, that's one thing. And moisture usually comes from warm air lifting up into the atmosphere and forming a cumulonimbus cloud like this one that's playing through here. So you got warm air, it's less dense, it's under low pressure, rises up into the atmosphere, forms clouds. And then if that develops over enough time and it has enough of a fuel source of warm, moist, rising air, then you can build a thunderstorm over time. You also need a lifting mechanism. So we talked about four lifting mechanisms. It could be density lifting, it could be orographic lifting, or what we call the rain shadow. It could be convergence lifting, or it could be frontal lifting. So you have to have those three ingredients: moisture, warm, rising air, and a lifting mechanism. So thunderstorms go through stages. The first stage is you have a cumulus stage. This is where you have warm air indicated by the red arrows here. You have warm air that's being lifted up into the atmosphere under low pressure. So as it rises up into the atmosphere, it builds clouds. It gets a cumulonimbus cloud that will get taller and taller and taller as it matures. And then eventually, once it has enough of a source, it'll go through a mature stage. So what a mature stage means is basically that the fuel that you have used to build this storm is now at the point where it starts to fall back down to the surface, and that would be the mature stage as precipitation. So you stop evaporating air or lifting air up into the atmosphere, it starts to come downward with the blue, higher pressure, colder temperature colors that we have here. And then eventually, if it stops taking warm air up into the atmosphere, that's usually what makes a storm dissipate. So the ground surface will go from pretty warm and evaporating and lifting air up into the atmosphere to then it dissipating because now the ground surface is cooled down because of the rainfall and it's lost that source of warm air that's rising to feed that thunderstorm. So it's going to dissipate. So if you're watching the animation through here on the bottom, warm air gets lifted up into the atmosphere, you form those clouds, it cools off, it condenses, it will rain back down. Now the surface temperature is cooler, so you lose that fuel source or that ingredient to build that thunderstorm, then the storm dissipates and fizzles out. So if we look at thunderstorms, then we also know that we can get thunder and lightning associated with it. What's kind of interesting about clouds is that they tend to act like a battery in a sense. So they'll have a positive and a negative charge in different locations of the cloud. Typically, the ground surface is positively charged, and what lightning is a connection, basically, of electricity between a positive and a negative charge. So if the ground is positively charged and the sky is negatively charged, what lightning is a connection between positive and negative. So here's another map for you. This is number of thunderstorm days annually. So let's look at Massachusetts. These are your first three quiz questions that you have. So how many thunderstorms does Massachusetts have annually on average? Question 2, which state has the most thunderstorms annually on average? And then which states has the least number of thunderstorms annually? So you should be able to answer all three of those questions based on the map that you're looking at here on the slide. So we got two more things to talk about. We're going to talk about tornadoes. I've personally never experienced a tornado, so I just teach about them, having never seen one myself. The closest thing I've seen to one is a typhoon, or not a typhoon. I can't even think of the word. It's like a little spinny cloud that will form over the ocean, and I can't even think of it right now. Anyway, so I've seen basically like a little spiral funnel cloud that's over the ocean that's similar to a tornado, but not quite as destructive. I'll probably think of it in a minute. All right, so let's talk about tornadoes. So we have this visual playing through of a tornado. So we know based on sensors that have been deployed from an airplane basically and tried to put them into an active tornado, that inside of the tornado, it's usually about 300 miles per hour. The wind is blowing inside of the actual funnel cloud. But then as it moves across the landscape, it's only going about 30 miles per hour. So at 30 miles per hour, you got this spinning cloud that's spinning 300 miles per hour across the landscape. Most tornadoes are pretty short-lived, so they can go travel 3 to 15 miles. There are some rare exceptions. So there was a tornado that traveled across Oklahoma in 1999, and it traveled across the entire state of Oklahoma, which is extremely rare. So most of them are short-lived, and they might travel 3 to 15 miles or so. Where do these come from? So we have to talk about our air masses again. So we had talked about like CT air and CP air and MT air and MP air. If you forgot what those are, you might need to remind yourself about what those are. But where our tornadoes come from and where Tornado Alley is in the US is where we have this clash of cool, dry air that's coming down from Canada. So that is our CP air, continental polar. So it's cold, it's dry. That moves south. And then from the tropics, we have warm, moist air from the Gulf of Mexico. So that's a MT air mass, marine, tropical, warm, moist. Those collide right over the center of the US. So we get these clashes of these air masses that couldn't be any more different from each other in terms of their properties. They clash right over the Midwest, and they're the ingredients for forming tornadoes. How that tends to work is that the cool, dry air is in the upper atmosphere, and it's moving slightly faster than the warm, moist air in the lower atmosphere. So, for example, that's why these arrows are different lengths. So, the upper atmosphere, that cool, dry air might be moving 25 miles an hour, and then the lower atmosphere, the warm, tropical air, might be moving 5 miles per hour. So, if they're both moving in the same direction, what you get is this rotation will form, and it will start to form this kind of spinning rotation due to the differences in how fast the upper atmosphere is moving compared to the lower atmosphere. Now, if that happens long enough, then you're going to get this kind of sideways rotation of the cool air sinking down and the warm air rising in a very short period. So that can form kind of a sideways funnel cloud that is parallel to the surface. And then all it takes is basically just a lifting mechanism, and you can get a tornado that will form. So it could take that kind of, and this is more just to show you what the actual atmosphere looks like. So it's not the actual funnel cloud as we think of it in this diagram here, but the point is to show you that if you just kind of lift that air up into the atmosphere, you can kind of cause this cylinder to turn vertical, and then now you have a full-blown tornado that has formed. All right, so now you have a full-blown tornado, and that tornado moves across the landscape for 3 to 15 miles. All right, so if you want just kind of a more written descriptive form of how a tornado forms, who would be a good figure for you to look at? And then just some visuals. I know we all know what tornadoes look like, but just a couple examples as it's moving across the landscape. It's maybe moving 30 miles per hour, but then inside of the actual funnel cloud, it's moving 300 miles per hour. All right, so just like thunderstorms, most tornadoes are going to have kind of a building phase or an organizing phase or stage, and then they'll mature. So the funnel cloud will come down, it'll mature, and then it's going to lose it's going to run out of energy and then dissipate over time. So this is that tornado that hit Oklahoma in 1999, but basically it's showing it traveling across the landscape as it started to organize. Then the funnel cloud touched down, it matured, and then it dissipated and decayed over time. How do we measure the strength of tornadoes? So it's the Enhanced Fujita scale, so EF scale. So it ranges from an EF0 to an EF5, and it's based on wind speed. So if you have wind speeds up to 85 miles an hour, that's an EF0. If you have wind speeds greater than 200 miles per hour, that's an EF5. And then it's ranked based on the intensity, so the amount of damage is going to increase as you go from EF0 to EF5. So for example, if you have an EF2, maybe the roof is torn off of a home is shifted off its foundation, mobile homes are completely destroyed, trees are snapped and uprooted, and cars can be tossed. If you have an EF5, that's considered massive or incredible damage. So well-constructed homes are swept away, steel-reinforced concrete structures are damaged, trees are debarked and then snapped in half. and you can lift trucks, like actual tractor trailers, off the ground in an EF5. So question 4 for your quiz. On the next slide, you're going to see 6 photos. So you got photos A through F. You're going to evaluate each picture as if you were an insurance adjuster. So you're going to play the role of insurance adjuster, and you need to decide what the category of the tornado is based on the damage that you're going to see on the next slide. So you're going to have to use the scale from the prior slide here, and then look at the images on the next slide. And then there are 6 categories, EF0 through EF5. There are 6 photos. So each category corresponds to one photo, and your job is to match up which photo corresponds to which category based on the Enhanced Fujita scale. All right, so what I want to point out is that tornadoes, the map here is showing you the number of tornado watches issued per year. So Tornado Alley is typically listed as like the Midwestern US, but most tornadoes tend to actually happen a little bit east of that, more in like the states of Arkansas and Louisiana, Alabama, and Mississippi, so more the deep south areas. But the US is home to a majority of the world's tornadoes, and we have about 1,200 of them that actually make that touchdown per year. So to finish up tornadoes, your final quiz question here is, why do you think tornado fatalities have declined in the past 50 years or so? So we have a timeline here looking from the 1950s to the 1990s, and then this is tornado fatalities in the US over that time frame. So the question on the quiz is, why do you think fatalities have declined in the past 50 years? So to finish up here, we're going to talk about not tornadoes. We just finished tornadoes. So we're going to talk about hurricanes. So that's our last kind of severe weather phenomenon that we'll talk about. So this is a aerial image from space of Hurricane Katrina when Hurricane Katrina made landfall in New Orleans in August 2005. At the point in time, it was the costliest natural disaster in all of U.S. history, the damage that was done by Hurricane Katrina. It's then been surpassed by Harvey in 2017. So hurricanes, we have before and after for Katrina. This is New Orleans here. And basically after that hurricane, a lot of the wards or zones within New Orleans flooded. And you can see the after here. So basically a lot of these homes were destroyed and then flooded over time. We have a coastal image here. So there was a house on the beach. And that house got moved away over time. We have this lighthouse, and then we have this bigger house here on the right side that got destroyed. All right, so there's a link to a video that I have for you to watch. It's a couple minutes long. So based on that, what are the ingredients for a hurricane? For question 6 on your quiz, what is the progression that a disturbance takes to form a hurricane? For question 7, and then question 8, what wind speeds are needed for a storm to finally technically be called a hurricane or Category 1 hurricane? So let's talk about how you build a hurricane. So the video discussed that you need certain temperature water. The video discussed that you need to have a certain couple of ingredients to build a hurricane, and then wind speed for it to be called a hurricane. So hurricanes are low pressure systems. So low pressure, just to remind you, is less dense air, it's warm air, and it's rising air. So a low pressure system is what a hurricane is built of. In order to get a hurricane, you need warm tropical evaporation and water that's a certain degree temperature, which you just learned about in the video. And that's the ingredients of the fuel source for a hurricane. So you get warm evaporating water up into the atmosphere. It will start usually as a tropical disturbance, and then it turns into a tropical depression, and then it turns into a tropical storm, and then it turns into a hurricane. So it takes time for a hurricane to form, and it takes about 2 to 3 weeks for that entire process to strengthen into an actual hurricane. So water evaporates from the ocean surface. You got warm evaporating water, and then you have cooler air up in the atmosphere. So similar to a tornado, you have winds going a certain way in the upper atmosphere, and then you have a source of energy or source of fuel from the surface. So the clash of this warm and cold leads to a rotation cell that will start to form, and then it'll strengthen over time if you keep having that evaporating warm water fueling the hurricane, and it will get bigger and bigger and bigger. So you'll have winds that will circle around a center location or a center point, the eye, and then you'll get rotation bands that move around that center eye or that storm. So what this looks like is that basically you'll have areas within the storm that are being fed by what's called this vertical flow or inflow of warm water evaporating up into the storm, creating clouds and creating these rain bands that circulate around a center eye. Around the center eye, you will have rising air, and that rising air kind of spirals around the center eye, and then that's what drives the movement or the spinning rotation of a hurricane as it moves across the ocean. Just to show you Katrina again, here's an example of the storm as it's going up towards making landfall. You can see the rotation pattern in the rain bands from this particular storm. So before a hurricane makes landfall, and what I mean by landfall is just that it crosses from the ocean onto land, it's either going to strengthen or weaken, which I know probably sounds silly to say, but many of them in recent times tend to strengthen. So with climate change, ocean temperatures are getting warmer. Warmer ocean temperatures equal stronger hurricanes because you have more of a fuel source for feeding that hurricane. So there's been a couple examples in recent times where a hurricane will be a category 2, and then overnight it can strengthen to a category 4 or a category 5 due to just excess warm moisture or warm water in the Gulf of Mexico for the ones that hit the US. So it'll usually strengthen in more recent times, and then as a hurricane gets closer to the US, so again, we're just focusing on the US here. These are all model tracks showing the potential places that a hurricane could go, but then once it gets closer, those models kind of tighten up and we do better at predicting where it might actually go. Once it makes landfall and it crosses from the ocean onto land, it immediately weakens 100% of the time. And the reason for that is because now you have friction. So friction of the storm crossing onto land slows it down. It loses its energy source, which is warm evaporating water. And eventually what it does is it just fizzles out. So if you have a hurricane, like this one here, this was Hurricane Florence that hit in September 2018, hit the coast of North Carolina and South Carolina. So it was a hurricane when it made landfall. Then it was downgraded to a tropical storm. Then it was downgraded to a tropical depression because it loses its fuel source. Now, if we categorize hurricanes, it is the Saffir-Simpson hurricane intensity scale. It's based on wind speed. It's based on pressure. So typically the lower the pressure, the higher the hurricane category, or the higher the wind speed, the higher the category. So it goes from category 1 to 5. If it's 74 miles per hour, that's category 1 hurricane. And then all the way up to a category 5 starts at 155 miles per hour. To finish up the quiz here, you have U.S. hurricane landfall locations between 1851 and 2004, and they're color-coded by category. Category 1 and 2 are blue. Category 3, 4, and 5 are red. So your next set of questions here. So approximately how many hurricanes made landfall in Massachusetts between 1851 and 2004? Question 10, which state has the second highest number of hurricane landfalls in the United States? And then question 11, which of the following states, based on the multiple choice question on the quiz, has the highest proportion of category 3, 4, or 5 hurricanes? So a big picture kind of summary slide here, weather systems can produce very severe phenomenon, tornadoes, hurricanes, thunderstorms, which we just talked about. But we've done better at forecasting in recent times and communicating how to get people out of the way, and then doing disaster relief and recovery after major events have happened. All right, so that's it for severe weather. And then all we have left to finish up is our unit on climate.